Hello and welcome to Easy Projects. So in this video we will finally take a look at the software that I used for my laser engraver or PCB maker that I showed in my latest video. I know I promised it would be up in a few days, but yeah, something got in the way. But it's finally here. So to recap, we use an Arduino Uno to control the whole thing, and we use an SD card from where we read a file, a bitmap file, and we use this file to determine where the laser should be on or off, and by scanning across the surface we can create the image on the printed circuit board or whatever you are going to use it for. So the SD card reader is an SPI interface, so we define which pins we use. Actually it's not set here, it's just a comment to let me remember which pins it is. We are going to use the libraries from Arduino, so we will use the SPI library and the SD library. We will need some way of converting pixels into millimeters, so we will need to know how many steps on the stepper motor we have per 1 millimeter, and in my case it's 25, so we just define that here. The stepper drivers that I use, they take a direction and a step input. The direction input, as it suggests, controls which way the motor should spin, and the step, every time you give it a pulse, it will take a step. So I just define the pins here, and I have an enable pin as well, just so you can turn it off so that the coils of the motor are not engaged when it's not in use. We will also need to home the machine, so I added 2 limit switches, and the input from that is defined here. And the numbers are just the pins of the Arduino, and the A5 and A4 is analog inputs. I just use them as digital though. We have the output pin for the laser on pin 8. So down here we create a file object, and perhaps I should mention this code is not written the proper way. But since it is all sequential, like it only has one function, the whole system, it's just written one thing after the other, but I should probably split it up into functions, and I will do that once I finish it. It's still in the prototyping stage. Anyway, we got the file object, which we need. And here we got variables for how far out the print head should move in the X and Y direction after we home it. So it will hit the limit switches and it will go to this position. Right now it's hard-coded, but I want to make a user interface for that if I get time for it. So I made 2 classes here, and we'll have to take a look at the bitmap file format to understand this. There might be some Arduino library that already has this built in, so you can just fill in the data. But I wanted to make it myself to fully understand how the bitmap file is made. So I named these classes fHeader and iHeader. The fHeader is the file header, and iHeader is short for information header. So there are some important things in here and some things that we do not really care about. So we got, for example, the file size, the width and the height. We also got color depth. You can have bitmap files in different color depths, so you can have 8-bit, 16-bit, 24-bit or 32 bits. I think the most common will be 24 bits, but we're actually going to use 32. But I think we should take a look at the bitmap files first before we continue on with the code. Perhaps I should also mention why I want bitmap files. I usually just print these out on a transparency and develop them that way. And with that I use PDFs, but PDFs are quite hard to read with a microcontroller. Bitmaps, on the other hand, are fairly easy. And the CAD program that I use is DipTrace. I really like that. And here we're looking at a 80 megasample ADC that I played around with. If we go to preview this, you can see we have a save option, and it can actually save as bitmaps directly. And you can specify the resolution here. This has to match the steps per millimeter that you put into your code. It's just DPI here instead of millimeters, but you can just convert it. So once I remove the correct things from the board here, I can just, with one click, I can get a bitmap file. So that's very fast. A good source for information about file formats is Wikipedia. It's a good source for many things. It's also a bad source for many things, but we can use it for this. So basically any file has a structure to it, more or less. At least images are very easy to understand, and uncompressed images like bitmap are very straightforward. If we scroll down here, we can see the file structure. We have some different headers here. You can see we have a bitmap file header and a DIB header. And then we have some other stuff here. And we have the pixel array, that is the actual image. So we'll go and we'll take a look at the bitmap header first. So first, if we look at this hex offset here, you can see it says 00. This will be the first thing we read when we open up the file and we read the first character. We can see it's 2 bytes long, so to get the whole thing we need to read 2 bytes. And over here we can see it is the header field. It is used to describe which information header is used for the file. There's different types, but I think the most common will be the BM, which is the Windows one. And my program is only supporting this one, but you could make implementations for all of these if you wanted. If this is wrong, then your program might not work. So you have to check this in your code. The next thing we will read at position 2, so after we read those 2 bytes, it's all given in bytes, by the way. The second thing will be the size of the entire file. That's handy to know, so we can see if we have enough memory for it. The next 4 bytes, so 2 by 2 bytes here, they are reserved. And finally we have an offset that tells where the bitmap image data or the pixel array is found. So that skips the information header. But we don't want to do that. We want to read the information header as well. But we can save this number that we get from here, and that points to the pixel array. So when we have read the information header, we can read from this number that we get here, and we'll start reading the pixels. If we scroll further down, we can see this is the Mac information header, and we go down here to get the Windows one. So here we get the size of the information header. You can see this is 40 bytes. But if we use the Mac one, you can see it's only 12 bytes. So there's a difference. But we will only be focusing on the Windows one. The next two are actually the most important ones. It's the width in pixels and the height in pixels. Then we have the number of color planes. It must be 1, so we don't really care about that. The next one is the color depth of the image. It can be 1, 4, 8, 16, 24 or 32. DipTrace stores it in 32 bits, even though there is no alpha channel actually. That's what the last one is. Usually in a 24-bit image you have 8 bits for the 3 colors, red, green and blue. But in a 32-bit image you have 4 channels. The last one will be an alpha channel. It's basically transparency that you can use. It's kind of a little bit fluffy because not all programs support this anyway. But yeah, DipTrace is putting out 32 bits. It is important to read this and get it right though, because it defines how many pixels you have to read every time you read 1 pixel. And then we have a compression method. This is also very important. We can see in a table which value corresponds to what, but we want this to be uncompressed for this program to work. We could also implement the decompression things, but it will be a little bit more difficult. Then we have the size of the image, so that's just the image, not the headers. And we have resolution of the image. This can be helpful, but in many cases it's not even set. It will just reach 0. And dip trace writes 0 as well. And then the last two, I'm not entirely sure what that is actually. A number of colors in the palette and important colors. It also says this is usually ignored. Down here we can see the compression methods, so we have to read a 0 here for my program to work. It's also the most common one. So when we have read all these headers and we have stored them in memory and checked the things that we want to check, we want to start reading from this address where the pixel array starts. So there is one important thing about bitmap files that we didn't see from the tables. You can imagine when we read this pixel array, we will read 1 byte will be one color, the next byte another color, third byte the third color in a 24-bit image. And there is nothing in the pixel array to tell you when the new line starts in the image. You have to know that by the width and the height of the image. But there is one catch. Each line has to be a multiple of 4 bytes, as you can see here. So if you use a 24-bit image, you can have some empty bytes at the end of each line. And you have to take care of that manually. So by the width of the image and the color depth, you have to figure out how many bytes of padding you will have at the end of each line. If you don't take care of that, you'll get a skewed image where the lines don't line up. So the pixel will be moved over like 1 pixel or 2 pixels for every new line, and you don't want that. Luckily with a 32-bit image, it fits nicely into groups of 4, so we don't even have this problem. It will always fit just by reading it, and there will be no padding. So in this exact case here, we don't need to think about it. Also, the colors can be stored in different ways, so we don't actually need to think about that either, because I'll be converting it all into the simplest form, should there be a pixel or not, so a 0 or a 1. And I'll just add up all the colors and set a threshold, so if it's above this, it's probably white, and if it's below this, it's probably black. Another important thing to notice is that the data in the bitmap file is stored in a little endian format, so the least significant byte is first. You want to keep that in mind when you store your data in memory, because if you only read 1 byte at a time, you have to put them in the correct order. We'll also take a look at that in the code. So to recap, we want to check the information header type. We got the size of the image, that could be handy, and we want to know where the pixel array starts. We then want to load in the information header so we can get the width and the height of the image. We use this to determine when to start a new line and when the image is done. We want to check the color depth. In my case, it only works in 32 bits, but we could make the program so it could take any type of image, so from 1 bit to 32 bits. And that's basically all we need to start loading the image. So the first thing we do in the setup here is to create an object of the F header that I made up there. I just copied everything from the Wikipedia site into variables here, so we can just store everything. I then set the inputs from the limit switches to inputs, of course. And I set pin 10 and the laser to outputs. Pin 10 is the chip select. I should have put that in here, but yeah, I didn't. And the laser is actually inverted, so 1 means off. I could have changed that also, but yeah. Then I make a serial connection to the PC so we can debug it at 9600 baud. So the first thing I want to do is to home the stereo motors. So move the motors backwards until we hit the limit switch. So we set both directions to 0. And the home switch is also inverted, so a low means that the switch is pressed. So we just continue stepping until we get a home signal and we stop. We do the same for the other axis. Then now we are at the home position and we reverse the direction here and we just move out the steps that we set in the variable up top. So 5 millimeters. These 2 loops will do that. I could have made functions for all this, of course, and it would be a lot easier to read, but I just made it as I went along. So that's us homed to the correct position, and we want to initialize the SD card. So if it fails, meaning there is no SD card, it will print a message saying that it failed, and it will return, so it will halt the CPU, just stop executing. Else it will say that the initialization is done. So we will open our file. It's just hard-coded to be test.bmp. I would also like to change this, so you can select it for a user interface. And we set my BMP equal to this. So we check if we got a file pointer. If this is 0, it means that either the file didn't exist or we are not allowed to open it. Then the first thing we'll do is to load the file header. So down here we will access the file header and we will enter a thing into this variable, and that's the iHeader type. And as you might remember, that's 2 characters. We should get a B and an M. And we basically do the same thing for all the other variables. So we get the file size and the reserved data and the start of the pixel array. But you'll see what I do here is I load the first one, then I bit shift the next byte 8 bits to the left. So we read the least significant byte first, then the next least, and so on, and we get the most significant lastly. So this is because of the little endian. If it was the big endian, we would have to do this opposite, so we would start with this one up here and 16, 8 and nothing. And we basically do the same for all the variables. So this is how we load them in. We just take them as they come and store them in memory. Again, you don't actually have to store the things that you don't need. I just did it anyway. And down here we start the info header. So we can see we get the width and the height, which we will need later. And we are done reading here. So just to debug, I print these variables out, or some of them, the ones that I'm interested in. And down here we start to actually draw the image. And this is very, very simple now. We make sure to set the correct direction for the y-axis. We don't need to change this at all when we're writing, so we'll just leave it. And one thing that I forgot to mention is that the bitmap image is stored upside down, basically. So the pixels are starting from left to right, but the line that is at the bottom of the image is the one that you'll read first. So usually you want to draw the image from the top and down, but the image is stored from the bottom to the top. So if you just start drawing it, you will have a mirrored image. There are different ways of dealing with that, but the easiest one, if you want to print it out, is just to mirror it in the opposite direction as well. So you mirror it twice and it will get back to normal. But what I did is actually I just draw it from the bottom up. So I just mirrored the y-axis on the stepper motor. So that way I essentially mirror it twice. So what I do here is I have 2 for loops, one representing each line and one representing each pixel in that line. So what we want to do we start with the first line and we set the x direction to 1, so we're going right. And then we go through the width of the pixels. So that would be drawing one line, a horizontal line. So I create a new variable called dot And this is used to store if there should be a pixel or not, so if the laser should be on or off. And I do this very simply by adding up all the channels of the image, so red, green, blue, and alpha. And if the sum of these are less than 513, I just pull the random number basically. We will print an X to the console, so this is just for debugging, and we will toggle the laser, so we'll turn it on, we will wait a little bit and turn it off, so we'll make a dot on the PCB. If it wasn't, we'll just print a space to the console, and we'll wait a little bit, but we won't turn on the laser. After we have done that, we'll make a step, so we move the X axis one step to the right, and we do this all over. We will of course get the next pixel when we read, and we'll check that, and so on for the entire line. When we are done with one line, so when this gets false, it will exit this for loop, and it will step the Y direction by one step. So we move to the new line, and we will home the X, or we will reverse the X axis back to 0, and we start over again. We will have incremented the Y loop, and we go through the X loop one more time, and we will do this for all the lines of the image, and then we're basically done. After that, we close the file, and we just go to an infinite loop. Nothing will happen. On the other hand, if our file didn't exist, if we got a 0 or null pointer, we will just print the message that we couldn't open the file. And again, we will go into a loop doing nothing. So I hope this wasn't too confusing. And again, if you want to watch the machine in working action, you can check the previous video. So thanks for watching this video. I hope you liked it, even though the code is not that pretty. But it is just one sequence anyway, so I guess it should make sense. I will do my best to get the last video uploaded as soon as possible. The one where I assemble the machine. I got it recorded already, and I just need to edit it. So until then, see you.